Let's continue, please. Continue. So the next speaker is Eugenio Ley-Koo.
Sí.
Ley-Koo. This is coming from Instituto de Física here in Mexico City, and he's going to talk about Lamé vectors, Spheroconal Harmonics.
This work is in collaboration with Ricardo Méndez Fragoso from the Faculty of Science of our university. First of all, I want to express our congratulations to Natig Atakishiyev for this opportunity. For this, well, it's in recognition of your important birthday and your important contributions to mathematics and mathematical physics. I have had the chance to be with Professor Natig and Professor Mesuma in a meeting in this Palapa in 2012 on superintegrability, organized by Bernardo Wolf and Paul Winternitz and Professor Miller. And I'm sure Natig was there too in the organization and in the symposium itself. And we also coincided in the group international colloquium on group theory in mathematical physics. Actually, when I arrived in the Centro Brasileiro de Pesquisa Física, me and my wife met and were welcomed by Natig and Mesuma. And in the previous one, in the University of Ghent, we also coincided in the G theory. And so we are well acquainted. Mesuma and my wife were doing the touring in Ghent, especially. Okay, so I'm going to talk about Lamé vector spheroconal harmonics. In the two G meetings, I talked about previous works that we have done with the spheroconal harmonics. And in the abstract, I will point out how we will be covering the material for this presentation, but also the work on which it is based. In the G30 meeting, we presented, well, I will just refer to the G31, basically a review of the development and application of the theory of angular momentum based on spheroconal harmonics. The spheroconal harmonics are an alternative to the familiar spherical harmonics. While the spherical harmonics are eigenfunctions of angular momentum, of the square of the angular momentum and the z component of the angular momentum, the spheroconal harmonics are the proper solutions for the rotations of asymmetric molecules, in which for the free case, L squared is still a good, a constant of motion, but there is no longer an axis of rotational symmetry. But the so-called Hamiltonian of the asymmetry distribution is quadratic in Lx, Ly, Lz, and with coefficients, let's call them E1, E2 plus E3, that are subject to two conditions. One is that the sum of them is 0, because from the complete Hamiltonian, in the metrics of the inverses of the moments of inertia, the trace has been subtracted. And this condition of E1 plus E2 plus E3, which will describe the distribution of the asymmetry, there is no trace left. And an additional condition is added that E1 squared plus E2 squared plus E3 squared add up to 3 halves. So we have two conditions on the 3 parameters, and therefore, if you give one of them, the other 2 are automatically determined. So this asymmetry distribution Hamiltonian commutes with the L squared and also with the complete Hamiltonian. And of course, this makes the corresponding Schrödinger equation separable in the spheroconal coordinates. The spheroconal coordinates, instead of using the parallel circles and meridian half circles to locate the points on the sphere, use 2 families of elliptical cones centered at the center of the sphere and with an elliptical cross section. And as coordinates, the corresponding surfaces intersect orthogonally. And so this we have studied, developed, and applied to different problems. And that's what we reported in the G31. And now we are going to the vector form of the spheroconal harmonics as the counterpart of the familiar vector spherical harmonics. And of course, we are going to use the case of electromagnetism to make the corresponding construction. So the constructions of the vectorial version of the spheroconal harmonics in their longitudinal, toroidal, and poloidal components is based on the use of the spheroconal harmonics as the bipotentials on which the gradient, the angular momentum, and the rotational of the angular momentum operators are applied respectively. So this is one of the things that we will be giving in the introduction. And then we will give explicit application. As an application, the solutions for the Maxwell equations of electromagnetism are constructed, illustrating the connections of sources that we restrict on the spherical surface with the potential and force fields inside and outside the sphere for the same multipolarity and complementary directions. And here are the references for our oral contribution in G31, and this is the written version on which we concentrated on the identification of shift operators and recurrence relations for the individual Lamé functions. The Lamé spheroconal harmonics are products of two complementary Lamé functions, polynomials, Lamé polynomials, in the respective spheroconal angular coordinates. So, okay. So this is simply a brief review of the laws of electromagnetism. And I know there are physicists in the audience, but there are also mathematicians. So I will very briefly give the, both the physical meaning, but most important, the mathematical connections between the sources and the potential and force fields in the electromagnetic case. So these are simply Gauss's law, the Faraday magneto-electric induction law. This is the Gauss's law for the magnetic induction field, and this is Ampere's and Maxwell displacement current. And we are including additionally the particular case of a time dependence which is harmonic with a frequency omega. And the Maxwell equations in its differential equation form also leads to the boundary condition forms in which the integration of this one for a Gauss pillbox on a boundary surface takes us to the alternative form that the normal components on one side and other side of the surface of the boundary surface is proportional to the charge density on the surface. Surface charge density. And the Faraday's law indicates that the tangential components have to be continuous. And for the magnetic field, it is the normal ones that have to be continuous, and the tangential ones are connected with the linear current density on the surface. And we will be using this in our presentation. And from the Maxwell equations, from the Maxwell equations, we can also connect with the law of conservation of electrical charge under the form of the continuity equation. And for the time harmonic dependence takes this explicit form. So the a divergence of the electric current density is proportional to the electric charge density. And from these two equations that do not depend on the sources, we see the possibility by integration that B can be written as a the rotational or a vector potential, and the electric field can be written as the time derivative of the vector potential and as the gradient of a scalar potential. So in the next one, we can uncouple the Maxwell equations and transform the linear first order differential equations into the wave equation, and the potentials themselves also satisfy the wave equation. So here we have the wave operator, and we have the potentials, and we have the force fields, and the respective sources. For the potentials are the density of charge, density of current, and here it will be the gradient of the charge density and the derivative of the current density. And notice the presence of the gradient here, and for the B, which can be written as the rotational of the potential, its source is naturally -1/c times the rotational of the current density. And here I want to point out, underline the appearance of the gradient, the appearance of the rotational, and this allows us to recognize the longitudinal character of one of the components of the electric intensity field, and J may have both longitudinal and transverse components, and correspondingly E will have also contributions from the density current, while the magnetic induction field has a source that is, from the very beginning, a transverse field. And of course, this is a consequence of the divergenceless nature of the magnetic induction field. And for the time dependence harmonic, simply the second derivative becomes the wave number, and we have Helmholtz equation for the four fields and their respective sources. We have here the gradient, but the time derivative has become simply proportional to the current itself, and there's no modification for the last one. So now I'm going to talk briefly about the Debye construction to identify the longitudinal and transverse components in its two modalities of toroidal and poloidal components. We start with scalar potentials, IL, IT, IP. These are the Debye potentials. And when we apply the gradient potential, we will have the longitudinal component of any vector field that you are dealing with. If we apply the generator of rotations, you will have the toroidal, which in the spherical case correspond to parallel circle lines for this field. While if we take the rotational, if we take the rotational of the generator of rotations applied to this IP for poloidal potential, we have the component that would be in the spherical case on meridian planes. So we are going to apply this for the sources to begin with, but then we will see the consequences through the solutions of the Helmholtz equation, the construction of the corresponding fields for the potentials and the force fields. So we have here the application. No. We have here the longitudinal component of the current and the two transverse components, the toroidal and the poloidal. And here we are using the I symbol to indicate that it's connected with the current, but we will be identifying along the way the corresponding components for the potential fields and the force fields. In particular, here we recognize that the continuity equation leads to the Poisson equation for the longitudinal, the bipotential, and the charge density volume charge density. And for the source of the magnetic field, we need the rotational of the density current, which we have to apply the rotational to this second term. But when we apply that, we have the IT toroidal component of the current, but it will become, of course, a poloidal component of the rotational of the current. And correspondingly, the rotational of the generator of rotations will have two terms, but the first term vanishes because it involves the divergence of the rotation of the generator of the rotations, and that is 0. And what we end up is with the Laplacian, the second term, with a negative sign, but now it will come in this form of the operator of the toroidal fields applied to the Laplacian of the poloidal, the bipotential. So this is the important part that in order to identify the three directions of the components of any three vector. And now we will systematically apply it for the potential fields and the force fields, in particular utilizing the green outgoing green function, which we are symbolizing with the G plus of R prime and R, including the case in which we have already used the harmonic variation in time. And now the next part of the introduction is a brief discussion of what the Spheroconal harmonics are and their structure. So we have what I mentioned at the very beginning, that the operators L squared and the Hamiltonian for the asymmetry distribution of the physical system, and these have the following quantum numbers. they have the L as the leading to the eigenvalue L plus 1 of L squared, and the indices A and B that correspond to the singularity removing factors in their corresponding Lamé functions. And those singularity removing factors also determine the parity of the solutions. This is because H star has Lx squared, Ly squared, Lz squared, that under the change of x by minus x, y by minus y, and z by minus z conserve the same form. So the eigenfunctions have a definite parity, and that information comes in these factors A, B, and N1 and N2 are these A and B have zeros that correspond to spherical cones, that, elliptical cones that have become degenerate into the Cartesian planes. And the N1 and N2 refer to the number of zeros that have the form of elliptical cones for the respective Lamé functions in one variable and the other. And here is the representation of this ket as the product of Lamé functions in the variables in the respective spherical cone coordinates. And they also have these parameters k1 squared and k2 squared that are connected with the eccentricity of the respective ellipses for the intersections with the Cartesian planes of the elliptical cones. And the N1 and N2 plus NAB, NAB can be 1, 2, or 3, depending the number of Cartesian plane nodes, have to add up to the L that is common to the two components. And the HN1A, HN2B are the constants of separation for the Lamé equations, and they are restricted by the conditions that their sum has to be the square of the angular momentum, and E1 HN1A plus E3 HN2B is the eigenvalue of the asymmetry distribution Hamiltonian. Okay, then we go on to the next one. And we are going to deal, now we are on the main body of the of our work, and is we consider Lamé spheroconal harmonic sources on the spherical surface. And I'm going to say at once that the harmonicity of each of the sources, but also their longitudinal, toroidal, or poloidal character will be shared by the vector potential and the electric intensity field. But the magnetic induction field will have the complementary transverse component, as I pointed out in the previous slide. So we are going to describe very briefly first the case of the toroidal linear current density distribution. And here you have the important part is that here we have the generator of rotations. And this is what gives to this current density its toroidal character. And this one is the explicit form of the rotation generator operator in these coordinates. We have a scale factor, and you notice that we have derivative with respect to He1, but with the unit vector in the direction of the other coordinate, and minus He1 second derivative with respect to the second coordinate. And this is to be applied to the Debye potential with the structure that we already indicated in the previous and here we have the toroidal vector electromagnetic potential, which has to be continuous at the boundary r equal to a. And here you can recognize this part is exactly the same that we have with the source of the potential. But we also are adding the radial dependence of the solutions of the Helmholtz equation in terms of the solution inside and the solution outside, in which r smaller and r larger are smaller and larger of the radius of the surface boundary surface, and r can be inside or outside. And here we have an illustration of the field lines. One of the, of course, the solutions for the fields inside and outside are solutions of the Helmholtz equation. And this leads us to field lines that can be described very easily and correspondingly can be plotted also. And this is the illustration for the current distribution on a sphere. We'll go on to that. And the electric intensity field is obtained by the time derivative of the vector potential, and therefore it also inherits the same character of being toroidal. But for the magnetic induction field, we have to get the rotational of A. And then, correspondingly, you can notice this has a minus sign. Here has also a minus sign because it is connected with the gradient operator. And no, I will go back. Okay, for the second case, I will just describe it very briefly because I do want to leave time for questions. In this case, the longitudinal current is obtained precisely using only the angular part of the gradient operator, because we want to confine the sources on the sphere. and therefore the radial component has to be eliminated. And in this case, in the previous case, since the divergence is 0, there is no charge distribution. This case is more complicated because with this current, we also have a corresponding charge density, which, of course, has the same Debye potential, but is a scalar. And from this, we can construct the corresponding potentials. The scalar potential shares the same dependence, spatial dependence, as the current charge distribution, charge density, plus or multiplied by the radial dependence. And the vector potential has this extra dependence because A and phi have to be connected via the Lorentz gauge. And so it is not only JH, but this extra term, so that A and phi have the, are consistent with the Lorentz gauge. And here it has the same character as the density current. And the two other entries construct the electric intensity field and the magnetic induction field, in which we can appreciate the, since we are going to have these derivatives, when we take the boundary condition, this will lead to discontinuities in the radial components, but which are connected and lead us back to the charge density current, charge density field with the same angular dependence. The tangential components can be seen that they are going to be continuous because they have the same radial dependence. And for the B, the tangential components are discontinuous and lead back via Ampere law to the electric surface current. And we have, do you have additional figures, or you want to show in the very first one, or no? No, the density currents were already displayed, but these fields, the potentials, will share the same distribution of the field lines, except on successive spherical concentric spheres, both outside and inside. And for the other field, the lines of force can also be calculated analytically, and then they can be plotted inside and outside. So I will give my presentation is ended, and we have time for questions.
So you have any questions?
Equations which you wrote down are explicitly Lorentz covariant.
Yes, yes.
Definitely.
Yeah.
So we usually used to then to express solutions as they transform properly under Lorentz groups. So we can characterize solution in terms of the Lorentz group. So your particular type of solutions, which are very interesting, what are they, if we try to characterize them in terms of the representation, say, of the Lorentz group?
Well, let me put this in context.
Okay.
Remember that we are on the path of saying we want to develop and apply the theory of angular momentum, but not on the familiar spherical basis, but in the spheroconal basis. The point is that this spheroconal basis, and I didn't say it explicitly here, but no, just in the conclusions, results and conclusions. The solutions in spheroconal harmonics constitute a new family interpolating between the solutions in spherical harmonics as the asymmetry parameters K1 squared and K2 squared change subject to this condition.
I understood.
And, yeah.
So you are using all the reduction on the subgroup related with rotations only, right?
Yeah.
And then,
Yeah, okay. The idea is that many systems are not spherically, do not have an axis of rotation. LZ is no longer a constant of motion. Okay? And for those systems, these solutions are more useful. Yeah.
But is there another constant of motion? LZ is not a constant.
H star, the asymmetry distribution Hamiltonian, is the other constant of motion.
Can it be expressed in terms of angular momentum generators?
It is E1 Lx squared plus E2 Ly squared plus E3 Lz squared. And we have identified the operators that connect all of the Lamé solutions.
This is very nice because I was trying to solve a problem. Maybe it has to do with something with phase space, two-dimensional phase space.
Okay. No, let me tell you a couple of problems that we are already addressing. We had the National Physics meeting at the beginning of October. And in the optics session, there was somebody who is studying scattering of light, not by spherical scatterers, but asymmetric scatterers. And when I saw that, immediately I went and told him, we have the proper tools to do that. So for the problem of scattering, and all of these are important. So we have, let me say, the Coulomb potential, the outgoing green function, all of these, we have the counterpart of the expansion of a plane wave and the expansion of the green function, not only in spherical coordinates that everybody knows, but in these alternative coordinates. So, and the chapter of vector spherical harmonics is part of any book, and we are with the intention of writing that chapter. Okay?
of extending.
Yeah. Okay.
Any more questions? So it's not the time.
Well, thank you very much.